So Brian, I'll pass it to you to dig a little deeper.
All right, thanks, Jeff. Okay, if you look at one of our data sheets, you're going to have different categories listed on there. Product models, there'll be specifications, information section, there'll be dimensional section, options, different connector types that you can choose from, and then accessories. So this section right now, we're going to be talking more specifically about the, as Jeff said, the meat and potatoes, the specification section. So next slide, there we go. So again, it starts off with the model. What is the load cell model? What are the available capacities for that model? And then also measurement units. Are you looking for pounds force? Are you looking for kilonewton? And then we get into the accuracy specs. It will be multiple specific aspects that fall under the accuracy umbrella, which I'll be touching on here shortly. And then we have the temperature in terms of what it can tolerate, how it reacts to temperature, and then of course electrical and mechanical properties for the sensor. So next slide.
This kind of
All right. All right, so looking at accuracy here, under the accuracy section, these are the common specifications you're going to see on interface data sheets as well as most other sensors. So nonlinearity, hysteresis, static error band, non-repeatability, creep, side load sensitivity, eccentric load sensitivity. Now, those last two you may not see on most other product data sheets, and you'll see it on all of our moment compensated load cell products. So, all right, let's go to nonlinearity. So nonlinearity, in a perfect world, a sensor is perfectly linear. So as you increase force, the signal tracks perfectly linear. Despite our best efforts, not every sensor is perfectly linear. So there'll be a nonlinearity spec that just captures how much does it deviate off that best fit straight, excuse me, off the straight line theoretical ideal environment. And units on that are going to be percent of full scale. Next slide. All right, hysteresis. So hysteresis is the difference in output on a descending load versus what the load cell produced on the ascending, or the sensor produced on the ascending. So what that means is if you increase load and you are increasing up to full scale, and then you hit one of the same points that you took on the ascending side, and you revisit that point as you're releasing the load, that output might not be exactly the same it was on the ascending side. So that's going to be defined as a hysteresis value. And that's going to be percent of full scale as well. So you can understand too, maybe that doesn't apply for my application if I'm only doing a single load and I want to track the force that's being applied through that test, right? So there's hysteresis. Next one. All right, static error band. This is something not all sensor data sheets have. A lot of them do. This is a good way to look at kind of a summary on performance for the load cell, and that's because it takes into account the nonlinearity on the ascending side, the hysteresis value on descending, as well as a non-return to zero. So it's actually as stated, an error band that encompasses all the deviation of output for that load cell in a test or in a calibration. And the SEB output is the best fit straight line within that error band. And we specify that SEB output on many of our calibration certificates. So again, if you're looking for an output that takes into account linearity, hysteresis, and non-return to zero, that would be the best output to use from a instrumentation calibration standpoint. So non-repeatability. Non-repeatability is essentially, as it says, how often or how much will a sensor deviate if you test it over and over again. Now, the key to note here is that's in identical loading and environmental conditions. So everything is being held constant. Typically, it would even be in the same installation. So you can imagine in the real world, you can't take this specification and assume that the sensor is going to be repeatable from test to test based on this specification. So this is a specification for stability. In particular, this is something that you're really looking for from a calibration grade load cell as well. So your reference standard, you want to have really good non-repeatability so that that sensor hits the same points every time, right? Next slide. Creep. So creep is a physical phenomenon that all mechanical and physical elements respond to. And essentially, it's a very slight change in deflection over time, even when you're applying the same load. So as far as a sensor is concerned, the creep spec would quantify how much the signal might deviate as you maintain that constant load. Now, the goal is that in the case of our load cells, which are foil-based strain gauge Wheatstone bridge elements, that the gauges are responding identically from a creep standpoint as whatever material they're bonded to, right? The key takeaway here is a couple. One is that it's a logarithmic effect. So most of the influence happens relatively early and then it decays over time. The interesting thing too is that it's easy to quantify typically in that it will respond or pull out of the system in the same way that it is introduced. So in other words, if you are doing a long duration test and you want to be able to get an idea of how much potential creep error might have been introduced to the system, as soon as you remove that load, you'll see a non-zero signal, and that signal will eventually decay back to zero in a mirrored behavior as the creep was introduced. So the other thing to note too, that pay close attention to the units. It's a percent of applied load over a time interval, and a lot of manufacturers won't always specify the same time interval. So even though you see two specs, they may look to be assumed to be similar. You got to take note of the time aspect. So Interface actually has a more aggressive 20-minute interval that we spec our load cells to. Next slide. Eccentric and side load sensitivity. So you'll find this on many of our products, or actually all of our products that are moment compensated. In particular, our low profile pancake load cells, or those of you familiar with Interface products, are 1000, 1100, 1200, 1600, 1800, 5200. We'll specify how sensitive the sensor is to non-primary axis loading, right? So for an axial load cell, it would be bending moments, it would be a torsional load perhaps, or a side load. So side load perpendicular, and eccentric, anything not perfectly concentric with the axis. So these are in percent or percent per inch. So pay close attention to that. And again, as Jeff alluded, we have a lot of specs internal and some that are on the data sheet that the units are tested to, right? And this is certainly one of them. In fact, most specifications on an Interface data sheet, every single unit is tested to. Others are design related, and we've got full confidence there. But every single load cell from Interface that has an eccentric or side load spec on the data sheet, it's tested to that. Next slide. All right, temperature. We're gonna do a little bit more of a zoom in here on temperature. It's important. Hopefully want everyone to come away today having a better understanding of how temperature affects load cells, and would be true for probably pressure sensors and other foil-based sensors, or strain gauge-based sensors, I should say. But there's a couple parameters: one, operating range; two, compensated range; and then the effect on zero and effect on span. So next slide. Operating range is as expected. This is the temperature range that the sensor can be operated in without any damage or anything that would be long-term. Now, pay attention that just because it has an operating range for that, you may see some error influence as the load cell or sensor is subjected to varying temperatures within that range. And so that's the next part here. So the next slide. Compensated range. So compensated range is the temperature range that we are guaranteeing the sensor to maintain temperature-related performance specs within. So you'll see in this example of the table there, operating range, -65 to 200, and we have a compensated range of 15 to 115. So the other thing to note too is a lot of most Interface products are a cold to hot compensated range. Competitors often will do room to hot. But the cold to hot is definitely flatter. And again, within that compensated range, it's going to maintain certain specifications. So on the next slide. So within that compensated range, we're going to maintain that the sensor will hit certain specs with regards to effect on zero and effect on output. So temperature is going to affect a load cell in two ways. One, it's going to affect what happens with the zero balance. These are ratiometric bridges, and ideally they maintain a zero value. But as temperature changes, the zero value might drift a little bit. So we specify how much it'll change, and it's a change per degree F. So it's a percent per change in temperature. And then the other aspect to keep in mind is the effect on output. So meaning how much signal are you going to have from that sensor, or how much change to your output will you see on the sensor through a temperature change. So you'll see over on the right there that the compensated range is essentially, you can think of it as a flattening of the curve within that range. And most of the time we're around 100-degree window that we compensate, tighten in for. Load cells certainly can be used outside the compensated range. It's not going to suddenly have a fall off a cliff in terms of what's going to happen to the signal or the zero balance, but you can imagine it's going to start to deviate, outside, of course, the specified range as soon as you get out of that stated value there. Important notes, though, and we're going to touch on this a little bit more too, is it's characterizable and it's repeatable. So how the sensor responds to temperature will be the same, and each unit's gonna be a little bit different. So we test every single load cell from a zero balance standpoint to make sure that it meets the temperature requirements. And even with the adjustments, we actually run them back through and do verification. That's another step that we do that a lot of competitors don't do. But it is important to note that temperature influence is repeatable. Okay, so there's a lot of characterization and testing that can be done to see how a sensor responds, and then adjust your test data accordingly. So next slide. All right, on the electrical side, there's usually a few things listed on the data sheet there. Rated output, so how much signal are you going to have at capacity? And that is millivolt per volt for most of our sensors. If that was amplified, it would have a voltage or milliamp rating there. Excitation voltage, this is how much voltage the sensor it can tolerate. We list a max value. Most sensors you're going to want to use about a 5 or a 10 volt. Running more voltage, not necessarily better. So the bridge resistance, most of our sensors are going to be 350 ohm. Some vary. It's a good thing to note if you're going to try to use a single instrument to run multiple sensors. You got to make sure that it's got the amperage to be able to push all those sensors. And zero balance, how much is the zero going to deviate from unit to unit, right? So we maintain most sensors that it's going to be within 1% of the rated output. Insulation resistance is a measurement of isolation of the bridge to the load cell material, and that'll vary also depending on the product. Next slide. On the mechanical side, so mechanical section is going to cover safe overload, how much force above capacity can it tolerate without permanent damage, the deflection, so that's going to be the specification of how much the load cell will move. There'll be a live end and a dead end, but how much total deflection, again, at the rated output or capacity if it's a full-scale cal. Most load cells are going to be very, very small deflection. You can see 0.001 inch in this case. Stiffer is generally better, but some lower capacity, some minis that we offer due to the design, get desired output, etc. You may have more deflection, so it's something to keep in mind depending on what your test requirements are. We'll list out if there's an optional base for that. So this is an LP, snippet from an LP. So we have a B101 kit. If you want metric thread, you would put the M on there. Natural frequency, again, this is correlating to multiple capacities within the a single model family. But that's good to note too if you start getting into dynamic or high cycle testing to keep in mind in terms of how stiff the sensor is. And then weight, calibration. Not all sensors get the same calibration, so you'll want to note, do you have a tension or compression? You can typically use sensors in opposite modes. They should be pretty symmetric, but again, if you want to have that specific mode cal data, you can always ask for it if it isn't standard for that model. And then material.